So let's talk about actually choosing a database. We've talked about a lot of different options: MySQL, MongoDB, Cassandra, HBase, and of course there's others as well. Maybe you don't even need an external database at all. So how do you make this decision when you're actually architecting a given system? Well, there's no real formula you can follow, but there are things you should think about, or at least things you should consider. It's not an easy decision. That's why people who make these decisions make the big bucks, but I can at least guide you through some of the considerations that you might make when making this decision as to what database, if any, you might need for your system. One thing to think about is what systems you need to integrate together. So different technologies have different connectors for different other technologies. For example, if you have a big analytics job that's currently running in Apache Spark, then you probably want to limit yourself to external databases that can connect easily to Apache Spark. Most of the ones we've talked about today can, but that's just one example. Maybe you have some front-end system that actually depends on having a SQL interface to a back-end database, and you're thinking about moving from a monolithic relational database to a distributed non-relational database. In that case, it might make life a lot easier if the non-relational database you're moving to offers some sort of SQL-like interface that can be easily migrated to from your front-end application. So think about the pieces that need to talk together in your system and see if they can actually talk together or not with existing off-the-shelf components, and whether those components are actually well-maintained and up-to-date. That might limit your choices right then and there. So it's the first thing to think about. Think about scaling requirements as well. So how much data are you really talking about? Is it going to grow unbounded over time? If so, then you need some sort of database technology that is not limited to the data that you can store on one PC, right? So you're going to have to look at something like Cassandra or MongoDB or HBase, where you can actually distribute the storage of your data across an entire cluster and scale horizontally instead of vertically. Think too about your transaction rates. How many requests do you intend to get per second? If we're talking about thousands, then again, a single database server is not going to cut it. You need something that's distributed where you can spread out the load of those transactions more evenly. Typically in these sorts of situations, we're talking about a big website where we have a lot of web servers that are serving a lot of people at the same time. If you're working at a really big technology web-based company, that's going to be the case. And in those situations, you need to be looking at distributed NoSQL databases more so than monolithic relational databases. Think too about the support you might need. So do you actually have the in-house expertise to spin up this new technology and actually configure it properly? It's going to be harder than you think, especially if you're using this in the real world or in any sort of situation where you have personally identifiable information in the mix from your end users. In that case, you need to make sure you're thinking very deeply about the security of your system. And the truth is, most of the NoSQL databases we've talked about, if you just configure them with their default settings, there'll be no security at all. Anybody at all can connect to these things and retrieve data or write data into them. So you need to make sure you have someone available who knows what they're doing for setting this up in a secure manner. That might mean, if you are in a big organization that has these experts in-house, that's great. Don't even think about it. But if you're in a smaller organization, you might want to consider, does this technology I'm choosing actually offer professional paid support that will help guide me through the setup decisions and the initial administration of my server over time? Or are there administrators that I can outsource the ongoing administration to over time? So in this case, a more corporate solution like MongoDB might actually be a good choice because they have paid support. And even for the more open source Apache projects, there are companies out there that do offer paid professional support for them as well. So do your homework and try to figure out, can I really do this on my own? And if not, what resources are out there in the marketplace to help me? Budget considerations, well, apart from the cost of support, you're probably not going to really be thinking about money very much because everything we've talked about so far is open source. It is free to use. You're going to be probably installing it on Linux servers where the operating system is also free. Really, we're just talking about the cost of the servers themselves here. So think about the cost of those servers. They can be significant in a large application or a large distribution. But apart from the cost of the servers, which, and these days you can rent that time too on things like Amazon EC2 servers or Amazon Web Servers, or Google also offers its own cloud services as well. In this day and age, budget usually isn't a concern when you're designing these systems because you can rent the time you need. Yeah, that will add up to something over time that you need to figure out what that's going to be. But if you're working for a company, odds are budget is not going to be your main concern in this sort of a decision. Something that you do want to consider, though, is the CAP theorem, our old buddy, where we need to pick 2 out of 3, consistency, availability, or partition tolerance. So again, the way to think about this is when you're thinking about the scale of your requirements, Do you need to have partition tolerance? Do you have sufficient scale where you know you're going to eventually need more than one server serving up this data, just for handling the transactions you're talking about and also for the scale of the data that you're talking about? If so, partition tolerance is non-negotiable. You need that one. And your only real choice in that case is consistency or availability. And that will determine which one of these sides of the triangle you might want to lean toward. So the type of application will determine what you want there. Only you know the actual requirements that you have for availability. Is it actually okay if your system goes down for a few seconds or a few minutes? If not, then availability is going to be your prime concern. Is it okay if you have eventual consistency where if you write something, people might get the old value back on subsequent reads for a few seconds? If so, who cares about consistency, right? Again, I would take availability instead. But if you're dealing with something that's dealing with real transactional information, like, stock transactions or some sort of financial transactions, you might value consistency above all else. And in that case, you want to really focus on that corner of the triangle. So again, understand how to read this diagram here. Cassandra, for example, lies on the availability and partition tolerance side of the triangle, where we're favoring these two over consistency. And when we talk about HBase and MongoDB, they are favoring consistency and partition tolerance above availability. Now, I should point out that the CAP theorem isn't really a hard and fast rule. I mean, it sounds like, dogma when people talk about it, but the reality is these trade-offs have become a little bit more loose in recent years. So, for example, consider Cassandra. Is it really trading off consistency for availability and partition tolerance? Well, you can actually configure the amount of consistency that you want from Cassandra. You can tell it, I want to make sure I get back the same result from every replica of this data before I actually consider that transaction to be final. And if you're running it in that mode, you're kind of getting all three to some extent. So this triangle isn't quite as wide or distinct as it used to be, in all honesty. The lines are getting blurred between these different trade-offs over time. So the honest truth is, any of these technologies can be made to work in pretty much any situation if you try hard enough. It's really a question of, choosing the technology that's best suited to the trade-offs that you want to make. Even with MySQL, for example, you can set up sharding still. You can still make it partition tolerant, but it's just more of a hassle and more of an administrative problem. And above all, my advice is always to keep it simple. So, if you don't need to set up a highly complex NoSQL cluster and something that needs a lot of maintenance, like, MongoDB or HBase, where you have all these external servers that maintain its configuration, don't do it if you don't need to. Think about the minimum requirements that you need for your system and keep it as simple as possible. If you don't need to deal with massive scale, don't deploy a NoSQL database if you don't already have one, right? Just use a MySQL instance somewhere. It'll be fine. So keep it simple. Do not deploy a whole new system that does not have good expertise within your organization unless you really need to. Simple technologies and simple architectures are going to be a lot easier to maintain, and believe me, you're not going to be happy when you're woken up at 2 a.m. because some random server went down on this overly complex database system that you set up for no good reason. So really, keep it simple, stupid. Simplicity is really the guiding principle that all of your architecture decisions should be based around. So let's look at a few examples, some fabricated case studies, and talk about how you might approach these decisions. So let's say that I'm just tasked with building an internal phone directory application. I want a little intranet page on my organization where I can look up phone numbers and email addresses of my colleagues. So in this case, we know the scale is going to be limited. I'm not ever going to have so many employees in my organization that I can't handle the scale of the transactions or the scale of the data. Even in a large company that has tens of thousands of people, you can store that on a single disk, without breaking a sweat, right? It's just not a big deal. Scale is not a big consideration. Consistency, it's not going to be the end of the world if somebody changes their phone extension and people get the old one for a few seconds after that update's been made. So consistency, not a big deal. Eventual consistency over the span of a few seconds or even a few minutes, totally fine. Availability requirements, you probably get some annoyed executives if this system goes down for any noticeable length of time, but it's not a mission critical system at the end of the day. But, of the things we've talked about so far, availability is probably the thing we care about the most so far. And let's think about simplicity as well. Odds are you already have MySQL installed on your front-end web server already. A lot of things run on what we call LAMP stacks, where it's MySQL is just part of the stack that you're building on top of. So you probably already have MySQL installed somewhere in your organization, and you most certainly have people inside your organization that know how to use MySQL and maintain it and administer it. So the choice here becomes pretty obvious. You would just go with MySQL, right? Because you don't need to deal with partition tolerance, and you care about availability, and it's already installed. People already understand it. So it's going to be a nice, simple solution where, you already don't have to worry about support very much because people already know how it works. It's simple, it's cheap. That's going to be the way to go for this sort of an application. Let's look at another example. Let's say I want to set up a system that mines my web server logs and tries to look for interesting analytical patterns. So imagine you're building like Google Analytics for your internal website or something. You want to answer questions like, what's the most popular time of day on my website? Or what's the average session length? Things like that. Well, how would you approach this problem? Well, first of all, step back and ask yourself, do I even have enough scale here to warrant a non-relational database at all? Why am I even thinking about this question, right? If all I'm doing is analytics, that's what Hadoop is for. That's what Spark is for. You can import this data into HDFS on your cluster and analyze it offline. We're not talking about high transaction rates here where we care about very quickly getting the answer to a specific query over and over and over again, thousands of times per second. That's the sort of problem that NoSQL databases are meant for. And if you don't have that problem, then don't introduce this new technology that you don't need. You could solve this problem just by importing your log data into HDFS, and we'll talk about ways to do that later in the course, but it doesn't involve external databases at all. Once that data is residing on my HDFS cluster, I can write a Spark job that mines that data, assigns the appropriate structure to it, and it can actually run machine learning algorithms on it, even using Spark's MLlib. So in this case, why would you have an external database at all? You can just use Spark. You can use tools like Hive and Pig. You can even connect something like Tableau if you want something more graphical. But there's no need here to set up an external database at all necessarily, unless you need to vend this data to a very large audience externally, right? So if you were actually building Google Analytics for real, where you had, millions of people that wanted to hit it and get answers from it at once, then sure, you'd want to expose that through some sort of external database system that's integrated with your cluster. But if you're just using this internally for analytic use, there's no need to even talk about things like NoSQL or Mongo or Cassandra or something like that. So the answer in that case would be none of the above. Just use your Hadoop cluster and the capabilities that the Hadoop ecosystem gives you without resorting to outside database technologies. Let's look at another example. Let's say I'm building a movie recommendation system. So again, I'm importing logs or some sort of customer behavior data, user ratings or something like that. And I might have a big Spark job or something else that produces movie recommendations for my end users once a night. The supposition here is that people's recommendations won't change very quickly, so computing them offline periodically is acceptable in this case. But you need something to vend that data to your web application. So, when a user comes to your website and says, I want to see recommendations, you need to be able to get that list of recommendations for that user very quickly. And let's assume that you're doing this at some massive scale, like you're Netflix or IMDb or Amazon or something like that, right? Big companies like that don't like downtime very much, so you do care about availability, but above all, it has to be fast. You need to make sure that it's not going to hold up the rendering of your front-end web pages. But you can give up consistency. So it's okay if for a few seconds after new recommendations have been computed for a user that you're still getting the old recommendations. So thinking back to the CAP theorem, we care about availability, we care about partition tolerance very much. The thing that we're willing to give up maybe is consistency. So in that case, Cassandra might be a good choice. If you look at that CAP triangle, Cassandra sits on that side where we're favoring availability and partition tolerance over consistency. And again, if you do care about consistency, you can still dial up the consistency meter on Cassandra if you want to. You can specify in your requests, actually, I'm willing to wait a little bit longer for a result that I know is consistent. So with that, let me kick it over to you. Let's do a little exercise and see how you would attack a given problem and choose a database. So let's imagine, if you will, that you're building a massive stock trading system. Wow, that's scary stuff. If you screw up, there's people's money on the line, right? People are going to be really upset if things go wrong here. So you care about consistency more than anything. If someone makes a stock trade, you need to make sure that subsequent requests reflect that data. You cannot have inconsistencies when you're dealing with a system like this. We're also dealing with big data here. So we do care about partition tolerance. We do have a lot of data here, a lot of trades, a lot of stocks out there, and it could exceed the bounds of what a single server could store or what a single server could vend, to the transaction rates that we expect to see. And it's all really, really important stuff. This is a case where security is tantamount. Whenever money's involved, you can pretty much guarantee that some hacker somewhere is going to try to break into your system and wreak havoc. So you're going to want to make sure that if you don't have the internal resources for addressing the security of a system like this, you have access to external resources that you can pay to guarantee the sort of support and security that you require. And you're going to have enough budget to pay for that support. Okay, so in our next lecture, let's talk about what the right answer might be. And there's really no right or wrong answer. There are more than one way to do this still, but think about the CAP theorem, think about your budget requirements, think about simplicity, and come back in the next lecture and let's see what you think the right technology choice might be for an external database for actually vending these stock trades to and from the public. See you in the next lecture.